Well, we're now in our last section of Chapter 1, Section 1.4, and we will look at a few more problems from this section. These problems focus on numerical accuracy of formulas that might look quite normal, things that you would use on your calculator. Nothing seems very unusual about them at all, except under certain circumstances, they can give you increasingly bad answers, even just flat out wrong answers, depending on how close to danger zones you get on those formulas. You don't usually think of formulas as having dangerous areas, but we will be looking at that in this section. Okay, so our first homework is making use of some formulas that you have very likely seen before in prior classes, particularly if you've had statistics. If you haven't had statistics yet and these formulas are not familiar to you, don't worry about where they came from. They're just formulas that we're going to use in this problem. So the first one is what's called the sample mean, or sometimes just called the arithmetic average. We sample n values, maybe there's 10, maybe there's 20 out of a larger population, and we name them. We'll call them x1, x2, x3, and so forth. And to get the middle of that, according to this particular measure, we will add them all up and divide by the total that's in the sample. Again, calling this the sample average. There's an additional metric called the sample variance, also known as the square of the standard deviation, which measures spread of the data. Looking at the clustering of the data, how tightly clustered these individual points actually are. The way you do that is you first calculate this sample mean, you take the difference of every one of the points and square those differences, add up the squares, and divide by one less than the sample size, and that's called the variance. Well, there's a second formula for it because it is identical to the first one. It doesn't look identical, but it will give you exactly the same numbers, well, unless you have some numerical problems. But theoretically, these are exactly the same formulas. So your first job is to prove that they're the same. Start with one and see if you can get the other one. Our second job will be to look to see if one of these two formulas would perform better numerically if the data is tightly clustered about the mean. Now we're going to assume a couple things. We're going to assume that the variance is very, very small. That's what we mean by tightly clustered about the mean. We're also going to assume that these x values are somewhat large in themselves, say at least 10 or 20 or something quite a bit bigger than 0. It doesn't say that there, but I want you to assume that also. Okay, so is one of those two formulas going to do better than the other one? Then we'll go to our second exercise, exercise B, and we're going to look at this little formula here, square root of x plus 4 minus 2, and ask what's going to happen when x gets near 0. Well, by now, since you've gone through section 1.4 in the lectures, you'll realize that the square root of a tiny number plus 4 is pretty close to the square root of 4, which is going to be very, very close to 2. So we do look like we're getting into the situation where we're subtracting two similar numbers. Okay, that's going to create a problem. So your job is to figure out a new formula to be able to fix that. There's two ways to solve this problem. We'll talk about that a little bit later in the hints. So that'll be your problem there. And finally, in part C, what's taken from problem 3 of exercise 1.4, this is the wording that I would like to use, and that is to provide a stable computational formula for the function e to the x minus e. And why might you get in trouble when x is getting close to 1? Those are the problems that we'll do, and we're ready now to look at some hints. So for the first problem, the one involving the mean and the variance, you need to be able to get from one formula to the next. I recommend starting with the one on the left and produce the one on the right. So here it is. Here's our formula on the left. And we will simply get to this other formula by doing some strategic algebra. I will get you started. You have to finish it. Square this out. What do you get? And notice that mu hat really is a constant by now. We've already done the averaging, and it is really just a number. Okay, so don't forget that. It's a fancy looking number, but it's still a number. If you do square this out, you should get something that looks like this. So make this your very first step. Well, we're starting problem 1 from your book, which is problem B here. And our problem was what happens when you have a function like the square root of x plus 4, and the square root term gets close to what you're subtracting it from. So our issue is you're going to be back to subtracting two similar numbers again. The square root of x plus 4 is going to be very close to the square root of 4 if x is close to 0, and we're going to be losing significant digits by subtracting similar numbers. This is how it's going to work. You're going to have a number that after you take the square root, which is very close to 2, it's going to have a lot of zeros in the significant portions of the mantissa, and when you subtract out 2, the only thing you get left over is the stuff to the right. The way our floating point works is we shift until we come to the leading 1, and that 1 is then next to the decimal point. We've simply plugged in a lot of zeros to the right. We've only got 9 significant digits here to the right of the decimal point, and so we are ending up going to be losing digits. If we had even a closer number, meaning x was even closer to 0, we would have lost even more. So this is a problem. Our job here is to fix the problem. So there's two methods that you can use. The first one is our good friend, the Taylor expansion. So go ahead and take the square root of x plus 4, do a Taylor expansion, but don't take it beyond the linear term. So find out what the constant is, find out what the linear term is. Then look at the error term and ask, will it get better or worse as x gets small? And I think you'll find it gets better, and you need to say something about why. So that will give you the first way to address the problem. If you do that, you don't have to do anything else. In your book also, there was a second way, and that is to use an algebraic manipulation that removes all subtraction, and that will fix the problem too. So how can you manipulate this formula algebraically so that you don't do any subtraction at all? So one of those two methods is sufficient. You don't need to do both. Okay, so now let's move on to the next problem. So let's look at some hints for problem 3. We have e to the x minus e, and the hint is, again, use the Taylor expansion for e to the x. There's really only going to be one viable way to solve this problem that I'm aware of, and that would be to use the Taylor expansion. So do a Taylor expansion for that, but what do you do with this e value? Well, it turns out that e is equal to e to the first power. That's the same thing as saying it's e to the x with x evaluated at 1. Well, that means that e to the 1 also has the same Taylor expansion as e to the x, except everywhere you had an x, use a 1. And that's really just use the same expansion. And then combine the two expansions, the one for e to the x and the one for e to the 1, and try to do some simplifications, and I think you'll find that a fairly easy problem to work.